We're going to work a few simple examples to illustrate some of the concepts that we've just reviewed for mechanical translational systems. Begin with a real simple case of a model that's been reduced to an ideal spring. And when we indicate the parameter like a stiffness on an ideal element, we're going to assume that what we have is a linear spring, right? So it's always going to be sort of the notation that we use. We have an input velocity, so a very simple system. Again, the point is to illustrate the use of constitutive relations and derivation of state equation if we need one. So do we need a state equation? Well, let's say, to illustrate, say we wanted to find, what is the force on the wall here that spring is applying. Since we're applying a velocity, in order to find that force on the wall, we know, because this is an ideal spring, that the force on the wall is equal to the force on the spring. And the only way we could find that is if we knew f sub k, which we know we can only find if we have that state x sub k. Now, x sub k is the deflection of that spring, and we don't know the deflection, we know the velocity, so we can find x sub k if we have a state equation. X of t equals v of t minus, if you like, the velocity of the wall. But the velocity of the wall is just 0, so that's 0. So our state equation is very simple. It's just this equation here, right? The only way to find x sub k is if we integrate. That means that we would need an initial condition at time 0, x sub k of 0, right? So we see that we would need a state equation for this very simple system. Now, to illustrate a case where you wouldn't need a state equation, consider the case where instead of the velocity as an input, you had some force applied on that spring. Again, to find the force on that wall, it would be equal to the force on that spring. Because it's an ideal spring, the forces are all transmitting across, so that f sub k is simply equal to f of t. So in order to find the force on the wall in this case, all we need to know is the input, right? The difference from that case. Now, that illustrates that we always know x sub k in this case, because we can find it by just inverting our constitutive relationship, right? So since f sub k is 1 over k times f of t, we don't need a state equation, which is a differential equation. All we need is the constitutive relation. And since we know the input, we know the state of the spring, right? We're going to call that a dependent element. And we'll talk more about that later when we're really studying bond graphs. But this basically says that, that spring is dependent on what's outside of it, which is, in this case, just that input f of t, right? Let's look at this other example here, which is very similar, except now we've got the spring in series, mechanical series, with a damper. Both are linear, right? It's just our linear spring relation, and our damper relation is a constant given here as b times the velocity of that damper, which is really the velocity of that end, minus the wall velocity, which again is 0, so it's just vb, right? Now, let's say again we wanted to find the force on that wall. Well, whatever this system is that we're modeling here, we've reduced it to ideal elements. Ideal springs and ideal dampers don't have any force, don't have any mass, so the force is transmitted across these elements and they're equal. So the force on that spring, right, is equal to the force across that damper. So we know that the force on the wall has to be equal to the force in that damper, which is equal to the force of that spring, right? So all of those are equivalent. What's different about all these elements is that they have different velocities, right? That spring has a different velocity than that damper, right? So a quick way to find the velocity of that spring, which we'll call x dot k, it's a state equation, is really just the difference between, this end, which is v of t, minus the other end, which is v of b, right? We can do that here by inspection, right? Just by studying the system. We don't have to do any complex kinematic analysis in this case. Later on, when we look at more complex systems, it can help to do some kind of kinematic analysis, but on some of these systems, you'll learn to just do this by inspection, and as we practice more and more, you'll get better and better at doing that. So the state equation, as we've started writing here, is x dot k, which is the difference between these two velocities. Now remember, a state equation on the right hand side can only be a function of inputs, in this case the velocity and states, but b is not yet written in terms of state. But because we know that the force on that damper F sub b is b times v sub b, and we know that that's equal to the spring force, right? That's an important equivalence. That's equal to k x sub k. We see that we can write v sub b in terms of xk, or v sub b is simply k over be times xk. And you can see that by just substituting v sub b into this equation, you'd get the final state equation for that system. Okay. Let's now use the basic mass spring damper system to illustrate a few of the methods that we're going to be using in the rest of this course. We have a mass here, so let's go ahead and begin by drawing a free body diagram. And I'm going to have a positive z-axis here in the vertical direction. We have gravity here, so we are going to have the mg force, so put that on there. We have an applied force, F of t, that's positive in the upward direction. And let's define the positive velocity of the mass upward. And this is going to be a single degree of freedom motion. It's only moving along one axis. And so we can see that as we compress the spring, we're going to have spring force and a damping force, FB. So as you can see, we have one mass. So remember that for each mass, we're always going to have, we're assuming it's a rigid body, so we're going to have a velocity associated with that. Again, one velocity for 1 degree of freedom. And we can then apply Newton's law for each mass that we might have in a system. So in that case, Newton's law says that the rate of change of the momentum, p dot, remember p is the mass times the velocity, so that's m v dot, right? So it's mass times acceleration, is the sum of the forces. In this case, the forces are, in the positive sense, upward, F of t, so you have minus Fk, right, minus Fb, and in this case, the gravitational force is negative, so it's going down. And always think about this, if it's working against the velocity, right, it's going to be negative, whereas the applied force here is actually going to be positive. So something that always kind of causes some confusion especially later, again, when systems become a bit more complex, it can be a little confusing. Should my gravitational force be positive or negative? And always, again, think about whether it's increasing the momentum. As you can see here, this is an increased rate of change of the momentum is positive with the applied force, whereas it's negative with the gravitational force. So this is the beginning of one state equation, right? And as in previous examples, we have linear elements here, so we know what the constitutive laws are. So we could replace each of these forces here with known constitutive relations, and those constitutive relations have to be in terms of state. The first one here, Fk, is x times the displacement of the spring, and the spring deflection is also going to be a state in this system, as we're going to see. And Fb, as before, is b times the velocity of that damper. Note that all these velocities are the same. That's something that you see in the way it's connected here. The velocity of the mass, because the one side of the damper and spring are grounded, they all have the same velocity. So the Vb here is actually the same velocity as the mass, so it's actually can be replaced by the momentum, right? P over m. So as you can see, you'd get this equation for P dot in terms of xk, right? And also in terms of P, and then you'd be done with that state equation. Then you'd need another state equation for the spring, but that one is easy because we know that the deflection of the spring, the velocity of the deflection of the spring, is also just equal to the velocity of the mass, right? And that's equal to P over m, and that's your second state equation. So here's your first, and here's your second state equation, and then you'd be done. We had a lot of discussion about these basic relations in generalized terms for Kirchhoff systems, where we wrote sum of the efforts equal to 0 and sum of the flows equal to 0. And just wanted to talk a little bit about those. These are going to be helpful, especially later. And it helps to see that these are common in all types of systems. And hope you can see that this equation, the sum of the efforts in this case is really sum of the forces equal to 0. But what you have to think about is that equation is basically, you know, the Newton's law equation, except what you have is that this equation is actually has that P dot term in there. So the P dot is, remember, an inertial force, so you can think of that being within that relationship. In this case, the sum of the forces, the sum of the flows, the sum of the velocities equals 0 does not apply here because there's only one velocity. So this is really more applicable when you have multiple velocities in a system where you have some kind of kinematic compatibility. But in this case, this sort of general relation relates to the Newton's law relation in this case. I've included this example because it was in the introduction to the course, and it fits in here with our discussion of a mass spring damper system to show you how you may begin, you know, with a real physical problem and have to reduce it down to a basic mass spring damper system, like I've sort of sketched out here. So here we remember we had this fan that had some an eccentric mass here because of some broken fan blades. So that was going to be inducing a force. It's a rotating force, so it's actually an XY force if you think about it, you know, in both directions here. But what we did was we assumed that it's very rigid. The base here was very rigid in the lateral direction, but could possibly vibrate up and down in vertical direction. So we modeled it in this form, in this schematic here, and we've represented this compliant base here with a linear spring, and also have included, even though there's no explicit damper, right, we are going to use an ideal damper to represent the fact that, you know, all materials we're going to have some loss effects. So we'd have to find, you know, what is the damping characteristics of this base, but there would be some damping here. At the end of the day, when you could then proceed to do modeling as we've just done as a mass spring damper system, if we have a positive force, say, going up here with motion, say, positive in the upward direction, the base stiffness and damping would be additional forces here. I'm not showing any gravitational force here. Sometimes in vibration problems, you may not put the mg force in there because you're just worried about motion about a certain point, and that equilibrium level could be found. The key part of this problem would be, how do you model, right, this force, this ideal force? And one way to think about it is, you know, you've got some, because of these fan blades over here, you have some eccentric mass. You'd have to come up with a representation for that here. The fact that it's got some eccentricity, got some effective mass, that's different from the total mass. In fact, I should be using a different m here, like the total mass here should be like a cap m, say, and this little m here would represent, so this would be the total mass, and this would be the eccentric mass that's spinning around. And that centripetal force, you know, would have two components, right? I mean, it would have a radial component, but as it's moving, there would be a component in the x direction, if you like, and one in the z direction. And the one in the z direction is the one that we'd care about. That's why I'm modeling this as f naught sine omega t. Omega t is really the angle that it's at, say, relative to this horizontal, and that force is that eccentric mass times the eccentricity times omega squared, right? That would give you the magnitude of the force, but then it would have a time component, so you'd have sort of a harmonic force forcing that base up and down. The dynamic model would be very similar to the one we just looked at for the mass spring damper system. Now I've included another example here with just two springs and a damper, and this is a example that's going to help us illustrate what happens when you need to determine whether all of the states of energy storing elements are whether they are independent or not, and that means whether they're actually a state of the system. And we know that the two possible states, because we've got two springs, are the two deflections here. So let's call those xk1 and xk2. Again, those are the deflections of these two springs, right? Are these both states of the system, or do we only need one? And how can you determine that? And later on in this course, we will introduce ways of determining that from a bond graph. But let's say you've got a system like this. How do you do this without those tools? And remember, we were also interested in, you know, what is that force on that wall? So again, that's one way to start thinking about the system. Remember, when you have ideal springs and dampers, these transmit force across them, and so we begin recognizing just from studying the schematic here that the force on all of these elements that are mechanically in series have to be the same. So we have to recognize that Fk1 is equal to Fb, that's equal to Fk2, right? By the modeling decisions that we've made. And in fact, that's also equal to the force on the wall, right? The the force that is generated in each of these elements transmits right through into the wall. In fact, if there's also, well, there is a force that you would, whenever you try to move this with velocity v, you're going to feel that reaction force back. To find that force, that's also equivalent here. So you can also say there's another force here that's called F. Okay. If you wanted to find how much power was being put into the system, you would need to find F. So we need to find these elements. Now, we need to find these force quantities. The fact that these are equal and that these are two energy storing springs means that we can identify that because Fk1 is equal to K1 xk1, that has to be equal to K2 xk2, which means that these two spring states, right, are equal. So only one of them is a state of the system, right? So only one is a system state, right? xk2 is the state of the spring, xk1 is the state of spring k1, but for the system we only need one of those to tell us, what is the actual state of the system, because once we know one, we know the other by this relationship. So how do we go about finding that state equation? Let's choose for our state xk2, right? We could just as well have chosen k1, but let's just choose k2, xk2. How do we find now a state equation for that? Remember, the state equation is the derivative of xk2, right? And that's the velocity here. Let's call that v2. So let's call this v1. Let's call this v3. And then we have the velocity of the wall, but that's just equal to 0, isn't it? Note that v1 is just v of t. So we have 1, 2, 3, 4 distinct velocities in this system. That's something that's important to identify whenever you're studying mechanical systems. So now we can use kind of our kinematics relation. We're just talking about that in another example. Remember, the sum of the velocity equal to 0. So there's a relationship here between these that we are going to be able to relate here. And by studying this basic system here, you should be able to see that you can write that v of t, right, minus, you can do it this way, you can do v1 minus v3, right? That's a velocity difference there, minus the difference v3 minus v2, and then that's that difference minus v2 equal to 0. You could write this a lot of different ways, and I'm writing it this way just because I want to show you that this right here, this difference actually is the velocity xk1. That's how fast that spring, spring 1, is compressing. This velocity here is the velocity of this damper, and this guy right here, right, is actually xk dot k2. So this relationship, in fact, is what's going to give you, by doing some rearrangement there, the state equation for x dot k2, and you can see that that's equal to minus x dot k1 minus vb plus v of t. Now, that's an input, that's not a state, and that's not a state. But remember, we can find both of these relationships from things that we know, right? From this relationship here, we know that x dot k1 is equal to k2 over k1 times x dot k2, right? And you know that VB is equal to FB over B, but remember FB is related to FK2, which is just k2 over B. So I'll let you finish this off, but you could, at the end of the day, write final equation for x dot k2 in terms of only xk2 and input. What you have to do is take this term here, move it to the left side, gather terms, and then divide through by quantities. What you'd end up getting is something that looks something like this. That's just a constant. And you'd have this term here, what is this, minus minus k2 over x k2 over b plus v of t. That's your final state equation. So you can see an example where you had two springs, but only the state of only one of them was actually a state of the system, right? And we're going to see problems of this sort later and look at other ways of handling them. What happens is as you can see, your algebra becomes just a little bit more difficult when you have problems of this sort.